This is chapter 13. Is this finished or not? This is not finished, na? So last week I finished RL circuits. Yeah. So this is RLC now. Then after we will discuss 17, chapter 17. Okay. So yes. So this is RLC circuit, girls, and what we learn, because we have learned discussed separately RL and RC. Okay, and just to review, in RC circuits, you know, the current in capacitor leads the voltage. We know that one, or we can say the voltage lags, right? So voltage lags there in RC circuit, capacitive, capacitor actually, and across the inductor, what is the situation? Voltage leads the current, right? And in capacitor, voltage lags the current, right? So this way, if we have all components present in a circuit, so here we can see that the current somewhere leads, current somewhere will lag, and R, we know that voltage and current is always in phase. So the phasor diagram is gonna be now something like that. What is that? So if we go for the impedance, what we call this one, impedance phasor diagram. So here we know that R is in positive X direction, and we already know that about the XC. XC is in the direction of VC. Voltage is also there, we know that one. This is also the direction of VR, correct? This is also the direction of VL. So this is about the capacitor. So capacitor voltage lags. So this is the voltage lags. So XC will also be in the same direction. But in case of inductor, voltage leads the current, this one. So this is also, and this is the direction of the current as well. We also know this one. So the point is that in RLC circuit, we can see that XC and XL, it is opposite in direction, or we can say it is out of phase. And how much it is out of phase? 180. It is 180. Now depending upon their values, if the values are equal, so because they are in the opposite direction, as well as the value is also equal, so it will cancel each other. So the thing is, both are reactance. We also know that one is inductive, another one is capacitive reactance. So here we need to calculate the total reactance. The total reactance, we can say X, for example, and it is what basically the difference of XL and XC. We can say absolute value of XL and XC. Then we will be getting the X here. Okay, and R is given to us here. Okay, so let's see now the cases, what will happen. So in order to, when we find the total reactance, okay, which is X, and or we can also say X total, which is the absolute value or difference of XL minus XC. So here is gonna be X. Okay, here is gonna be X. This is the value of the X66 here. Also, we can see few more concepts here. Now we know X, so just draw the parallel of this X here, and this is the R. Now girls, we can also find the total impedance or the impedance of the circuit. So impedance is gonna be Z here, and formula we already know that Z is equal to R square plus XC square XL square. But in this circuit RLC, we already calculated the X. We will be using this total reactance. We will put it here. Now we can get the value of Z. Now this is the Z, which is the impedance triangle for the given RLC circuit. And this is the phi, which is what? Phase angle. So phase angle is equal to, what should be the formula for the phase angle, girls? It is tan inverse. What it should be? Tan inverse Yes, X over R. This is X over R. Yes, formula we know already. Either it was XC over R, XL over R, but here we are using X, yani total reactance or resultant reactance, because they are opposite direction. So something. Now girls, just assume if XL and XC both are equal. Both are equal. What will be the value of X at that time? 0. So if it is 0, so let's suppose here, if it is 0, so what will be the Z? Impedance. Impedance will be R, right? Impedance will be R. It means is that the capacitor will behave like a resistive circuit. Am I right? The circuit will appear to be as a resistive circuit. So the thing is, this is some interesting factor which we will learn now. Okay, so actually there is a situation when both of them can be equal, and that frequency, actually at a particular frequency, both reactances XL and XC could be equal, and that frequency is called resonance frequency, or with that condition is called the resonance condition. We will also discuss that one. Also, what about the theta when we say X is 0? So when you put this is 0, girls, so tan inverse theta, which is tan inverse 0, it is gonna be 0, correct? Yeah. So where should be the Z plotted at that time? Z will be plotted in the exact direction of R. It will be exactly equal also, right? This is like Z direction. So Z is here, R is there, and vector is also of the same value because Z is equal to R, and there is no phase difference, yani, so theta is also 0. This is something. So let's see now this condition. So here see the RLC circuit, girls, and one more thing, when a circuit contains an inductor and a capacitor in series, the reactance of each tends to cancel. This is the tendency actually. Both the reactants try to cancel each other. As you can see that one reactance is in positive Y direction, another is in negative Y direction. They will try to cancel each other. So we can get it the total this way. Now the total impedance can be calculated by this formula, and the theta will be X total over R. Now guys, the variation of both reactances with respect to the frequency. So x-axis you can see the frequencies here, and on y-axis we have reactances. So see, this is xc. Do you remember the formula of xc? What is xc? 1 over 2 pi fc. So hope you remember what will happen if we increase the frequency. 2 pi fc. By increasing the frequency, xc will decrease, right? So which is here? We can see here it is now decreasing this way, right? Now this is about the xc, and look about the xl. For the xl, yeah, for the xl it is 2 pi fl, or 2 pi fc, 2 pi fl, sorry. So here we know that by increasing the frequency, the value of xl will increase. So that's why it is a linear relationship, right? So this is for xl, this is for xc, right? Can you find a point where both xc and xl are equal? This is the point, correct? This is the point where both are equal, and the frequency at which they are equal is called resonance frequency. And this condition, when xc and xl both are equal, it is called resonant condition. Okay, let's see now this one. At a frequency where xc is equal to xl, the circuit is at the series resonant, and here is this one, they are equal. And See this one. Another thing, read this one. Below the resonant frequency, the circuit is predominantly capacitive. Because here below this frequency, what happening? Which is greater, XC greater or XL greater? You can see from the graph, both graphs. What is greater, XC or XL? Left side of this point, XC. So if XC is greater, what happening at that time? Because XC is greater, yani circuit is behaving like a capacitive circuit. Getting the point? So because of XC is greater, it is behaving like a more capacitive circuit. Now the opposite case is here. If we go to the right of this center frequency, this is called resonant frequency. If we go here, so here you can see which is greater, XL greater or XC is greater. You see XC is reducing, but XL is increasing. Yani in this situation, what happening? Above the resonant, the frequency, the circuit is predominantly inductive. You can see the green area is here. After this frequency, if we increase the frequency beyond that, the circuit will behave like a more inductive, because capacitive reactance is less, so capacitive effect is less compared to the inductive effect, so the circuit will behave like a more inductive circuit, and this frequency is called the resonant frequency when both are equal actually. So here is a question which you can solve. What is the total impedance and the phase angle of the series circuit? R is equal to this, XL is equal to this, X is equal to this. So guys, it's so simple. What you need to do first, calculate first X total, yani X, or we can say, then calculate this Z total, R square plus, something like that. After that, you can calculate the phase angle. Theta is equal to this one. Now girls, if I ask you, is this a capacitive circuit or inductive circuit, how this circuit will behave? So how can you tell that one? And what is the answer for that? Circuit is capacitive or inductive? Okay, XC is greater than XL. So inductive or capacitive? Capacitive, right? Because of XC is greater than, so circuit is behaving like a capacitive also. So in capacitance, do you know that current leads the voltage, right? In capacitance, current leads the voltage. So what is our statement now? The circuit is capacitive, so I leads the V, and how much it will lead? This much. Clear? For example, if I interchange these values, XC by XL, what will happen? Circuit will be inductive, because of if we interchange more inductive. So if inductive, so I will say the circuit is inductive. So what I will be writing here now? Yes, correct. We can say then voltage leads current by this angle. Or I can also say one more thing, I lags, V by this one. So this is the statement. It depends upon whether the circuit is behaving capacitive or inductive. See now, what is the magnitude of the impedance for the circuit? Magnitude of the impedance, yani Z. Okay, for the Z, what we need? We need XL, we need XC, then we need what? X. So get the absolute value, the difference, then we can calculate it like this. This is the Z here, magnitude. Okay, and see the frequency is 100 kilohertz. Okay, and you can see here XL is greater, so circuit is inductive here. No, XC is greater, so circuit is capacitive. Circuit is capacitive, and frequency is 100. Okay, now impedance over this one, yani let's consider that Depending on the frequency, the circuit can appear to be capacitive or inductive. The circuit in example 2 was capacitive because the frequency is towards the left of the resonant frequency, right? We know that it is less than that one. So what we try to do now, let's increase the frequency and see what will happen at that time. So again, resonant condition, we can just recall to I already explained to you. So resonance is the series RC circuit. In a series RC circuit occur when the capacitance and the active reactances are equal in magnitude. Yani if this is the situation, it is called the resonant condition. And in this condition, what we will have, Z is equal to R. Also X and a difference will be 0. Phi will be 0. You know already this thing. Okay, so this is what they are showing here. Now another example, girls, we increase the frequency to 4 hertz, kilohertz, not the, it is 4 kilohertz. It is shown here. Earlier it was 100. And we increase the frequency. Let's see now what happening. What is XL and XC value? So when you see here, XL is now greater than this one. It means circuit is going to behave like an inductive circuit, and the Z is 786 here. Okay, right? Yeah, it is inductive like. So because it's depending upon frequency, what I want to show here. So by changing the frequency, the behavior of the circuit is also changing. This is the point actually. So what is that? The circuit is now inductive because earlier frequency 100, now 400, it is now inductive. Now by changing the frequency, the circuit in the example 3 is now inductive because of the reason XL is greater than XC. We know that one, right? Because it is like that. Now this is about the voltage phasor, which I already explained to you. This is the direction of VR, VL, and VC, right? You have idea already about it. Okay, so just move next. Voltage in series RLC circuits. This is something interesting. So as we have seen that again, the VL and VC both are in opposite direction, girls. Okay, and VR is in the direction of the current. We know that one. So the voltage across RLC component must add to the source voltage in accordance with the KVL. We know that KVL, Kirchhoff voltage law. If we have a series circuit, the total voltage will be the sum of the all individual voltage drops. So because of the opposite phase shift due to L and C, VL, VC will effectively subtract. We know that VC is going towards negative Y, VL is going towards positive Y. So they will subtract, they will cancel each other actually. So see this interesting, what you call waveform. This is for VL voltage, and now this is VC, girls. VC is basically opposite. We know that one. But the value will depend upon how much it is. So now we know that in order to know the total voltage, basically effective voltage, so when they will add together, so what will happen, because VL is positive at the peak and VC is negative, they will cancel each other, right? So after cancelling, we will be getting some resultant voltage, which is something. Notice that VC is out of phase VL. When they are algebraically added, the result is gonna be something like that. Is it true? Because VL is greater, VC is less, right? So we will be having something here more positive, correct? And here this is negative is more compared to the positive. It is gonna be. So this green is basically what we call composite or overall voltage drop across both of them. Yani it is the sum of their voltages, which is green. It is like that. Now, girls, let's suppose both voltages are equal. VL is equal to VC. Okay, let's see now. So if this is the case, see, though they was already opposite, out of phase, now they are equal also. What is gonna be now? So at that time, the voltage which is gonna be dropped across these two, it is gonna be 0, right? If it is 0, so the circuit will be purely resistive at resonance. And when it will be equal, we know that that condition is called resonance. So at resonance, circuit will behave like a purely resistive circuit because there is no drop across these two components. It is showing here as a 0, right? So circuit will behave like a purely resistive circuit. This is the concept here. So algebraic sum is 0. Now guys, another thing is that we know that the condition of resonance, what is the condition of resonance? We call that the both yani XL is equal to XC. We know that 2 pi FL is equal to 1 over 2 pi FC. Guys, just cross multiply. When you cross multiply, you will get F. We will give the name FR, and it is equal to 2 pi under root LC. This is called condition of resonance. Okay, so yani if you want to know at which frequency XL will is equal to XC, you need to just apply this formula, put the value of L and C, 2 pi, and you will get that frequency at which XL will is equal to XC. Clear girls, this formula also? Okay, so this is called resonance frequency formula. Okay, let's see. What is the resonant frequency for the circuit? So simple, just apply the formula, get it. And what I found, at 196 kilohertz, okay, the circuit will behave like a pure resistive circuit because of XL and XC will be equal at that frequency. This is the way, okay, to understand this. Okay, rest is what? In series resonance, ideally resonance, the sum of VL and VC is 0. We have seen that if it is 0, so if you apply KVL, so can you say that VR is equal to VS? Yani total voltage which we are applying is going to be drop across the resistance, because the sum of the voltage which are here, it is going to be 0 because they are equal and opposite. You can also see the signs here, right? So let's see. Question, what is VR at the resonance? So you don't need to look here anything, but question is clear. What is the VR at the resonance? So condition is given resonant to you, and we know that at resonance what happened, there will be no voltage drop or the 0 voltage drop across the combination of L and C. So the total voltage which you are applying is going to be drop across the resistance. So how much it will be, girls, then? 5. Yeah, so sure, you don't need to calculate anything. Yeah, it will be same. Yes, you need to look only across the R, because here it is gonna be 0. So here you don't need to calculate, but the concept is there. Resonance, this is something, right? So this is here. So now this is the impedance curve as Z1, and we can see at resonant frequency what happening. Z is exactly equal to R, right? This is the overall here. So summary of important concept for the series resonance, girls. First point, what we learn, capacitive and inductive reactances are equal at resonance. We know that one, right? Also, total impedance is minimum and it is resistive. We also know that Z will be equal to R only. It means it is minimum. Okay, so total impedance will be minimum. Girls, if impedance is minimum, what will happen to the current? The current, impedance is minimum, it will be maximum, correct? The current is maximum. So this is, series resonance concepts are coming one by one. Current is maximum. So phase angle between Vs and Is, phase angle will be 0. Why? Because it is behaving like a purely resistive circuit, and purely resistive circuit, voltage and current always in phase. They are in phase. So here is phase angle 0. Also, FR is equal to, given by FR, this formula 1 over 2 pi LC. And this is just summary of this chapter. So this is done now. Okay, let's do one thing else. Just have a break, finish the prayer, and then we will start after the break. So I'm also going for the prayer, then we will start it. Okay, maybe 15 minutes. I'll go, then I will go back. Okay, so yeah, you can also have a free, and if you have question, we can discuss later on. So 15-minute break.